In the 1960s, NASA engineering know-how laid out some special procedures that got America to the moon. One procedure focused on saving the lives of astronauts in the event of a launch emergency. A launch escape system was used on both the Mercury and Apollo programs. It was capable of aborting during an emergency while the launch vehicle was on the launch pad and for most of its ascent. Primarily, it used a tower configuration. But due to technological limitations of that era, there were several blackout zones during which a successful abort was not possible. Now, let's fast forward 30 years.
When it went off, it was just, breathtaking. I could not believe just how perfectly it looked like the simulation.
Our agency has a diversity of skills and capabilities across multiple centers. Obviously, the Johnson Space Center focuses on the manned aspect of spaceflight. Marshall Space Flight Center focuses on the propulsion, the launch vehicles. It was actually a real joy, I think, for this team to come together and gel.
Today's Orion spacecraft program studied the systems of the past to develop an optimum and efficient abort system for the current vehicle. From their studies, researchers developed the Launch Abort System, or LAS. The LAS is designed to provide abort capability on the pad and through much of the power ascent.
We've got 3 motors on the Launch Abort System. We've got the big motor, the abort motor, 500,000 pounds of thrust in 1.5 seconds. We've got the jettison motor, which has to operate in every flight. It's the nominal mission, which has to get this whole structure, this whole system, away from the capsule when it's on its way into orbit. Then we have the attitude control motor, which I say that with a smile, which has been our problem child, with 8 pintle valves, state-of-the-art, never been done before.
The attitude control motor is a very complicated motor. It has 8 valves around the perimeter. And it can actually vector the thrust in different directions so that it can actually drive the vehicle along a trajectory as it flies away very rapidly. And then there's the jettison motor, which actually is used on every flight. Basically, if there were an abort, the jettison motor would be used after the abort motor has burned, and then the vehicle is reoriented with the capsule forward. And then the jettison motor jettisons the launch abort system off of the crew module and allows it to deploy its parachutes and then land softly.
The LAS performance, control, and capability far exceeds anything fielded to date and takes advantage of many cutting-edge breakthrough technologies like the weight-saving abort motor case is the first composite solid rocket motor case ever used on a human-rated system.
One of the most significant challenges during the fabrication process was the employment of an advanced composite material in the attitude control motor valve assembly. The pintle and the pintle guide were fabricated using a new carbon-carbon silica carbide material that had never before been used and never before been applied to this kind of duty cycle. And so we were quite concerned about its success. We preceded the Pad Abort 1 flight with 2 full-scale ground tests of 8, each motor encompassed 8 valve assemblies. Both the ground tests were successful, which gave us good confidence that was borne out by the success of Pad Abort 1.
The first ever use of a reverse flow abort motor on a U.S. crewed system, which improves safety by diverting the exhaust away from the crew module.
The abort motor is a remarkable motor in the terms of reverse flow design and 500,000 pounds of thrust for 2.5 seconds. That's a wild ride. So it came together quite well, and we're really proud of that motor.
And the first ever throttled solid rocket motor control system in the several thousand pound thrust class. Along with employing more composite materials than the world's most advanced fighter jet, the F-22 Raptor, the Orion spacecraft saves significant mass. These design configurations make the LAS a performance winner.
I think from the project perspective, one of the challenging things was as we got closer to launch and we were trying to do our final verification of requirements, which is where we basically say this vehicle is ready to go fly. That was certainly a challenge just because we had so many requirements we were trying to verify. We also had some issues where we had some waivers to requirements, and just processing those and really understanding the technical details behind that and what the risk was in accepting those waivers and what that means to the launch.
We looked over thousands of requirements, thousands of verifications. We looked over data sets after data sets, trying to look through this design review and that design review to make sure that we didn't forget anything, to make sure that this bird was going to work.
Using solid rocket propellant more powerful than the Atlas 109D booster that launched astronaut John Glenn into orbit in 1962, the newly designed LAS Abort motor generates more than 1 million pound-seconds of total impulse during a fast and furious 6-second burn.
I think the major I won't say obstacles, but we had to meet the agency's requirements, prove to the agency we're ready to fly through a series of readiness reviews, and pushing the paperwork through to meet those, I'll say, those checkpoints was probably the most difficult to drive people towards. I think to get the momentum behind the team, to know exactly what we had to do and when to do it. And it took a lot of people pushing and pulling in the same direction.
You know, you have a definitive product at the end, and you have a goal, and something will be launched, and thousands of people are watching, and there's a lot of money investment, there's a lot of people investment, and you want it to go right, and you want NASA, the agency to look good, and the project to look good, and your center to look good.
The Launch Abort system accelerates the crew module to nearly 500 miles per hour in just 2 seconds, with an acceleration of 16 times the force of gravity.
Most challenging aspect for structures is always loads. Getting a well-defined and well-understood load set. With any project, loads evolve through the course of the project, but for this project it was unique in that this vehicle has never flown before. This is a first-time flight of this combination of motors. And so the loads were all analytical at first, and so they were evolving over time, and we designed the structures and looked at our margins of safety, make sure we could survive those loads. And then probably the other big test that we did, in addition to the structural test, was the modal survey. And what was critical about that is that the guidance and control group gave us a target that they wanted that frequency to be within a certain range. And again, the team had really put together a great model for that, because it came out that the measured frequency was very close to what was predicted, and only a few minor tweaks had to be done. So that was a milestone that we had to get that test and make sure that we satisfied the guidance and control folks.
In a spectacular test, NASA demonstrated a new astronaut escape system in New Mexico, boosting a crew module simulator more than a mile up in just 20 seconds and parachuting it to a safe landing in a demonstration of how future astronauts will be carried to safety in the event of a catastrophic on-pad launch vehicle failure.
I think it should be noted that this Launch Abort system was developed on a very ambitious and aggressive schedule. Attitude control motor obviously was our most complicated technology. It didn't exist before we built it and flew it. And so when we actually fired the first full-scale static test motor, I personally was elated. I mean, it was a significant accomplishment for the team. It was a significant accomplishment for human spaceflight.
The Abort motor burned for approximately 6 seconds, boosting the system to an altitude of nearly 4,000 feet and putting it on a ballistic trajectory with a predicted high point of roughly 6,000 feet.
This motor is unique. It has a 4-degree thrust offset. That means if you fire the motor, it doesn't fly in a straight line. It purposefully is always going to veer at 4 degrees. And the way they do this, they Aerojet designed the motor to have one nozzle. That's a little different than the other 3. And this helps you in getting the two pieces of hardware in different places in the sky so that they don't run back into each other. You do not want to recontact.
The attitude control motor with 8 computer-controlled thrusters helped to maintain the craft's stability during the initial climb away from the White Sands Missile Range launch pad.
The technical challenges is, from I guess a flight dynamics perspective, is working on an actively controlled launch abort system. So our launch abort system, unlike Apollo, has the ability to actively steer the system, and that greatly improves the overall safety of the vehicle, improves the chance of saving the crew. So working on that, making sure that was working and that there were no issues with that, and also, as I said, maintaining good coordination and communication with a large team across multiple centers and with a contractor.
Of course, then that leads up to, May 6, 7 a.m. Mountain Time, and the LAS launched and went through the complete profile flawlessly.
10 seconds after takeoff, the attitude control motor repositioned the vehicle to a capsule-first orientation, and the burned-out escape system was jettisoned away. Drogue parachutes deployed to slow and stabilize the capsule before 3 116-foot wide parachutes unfurled for the final descent.
I mean, it was operating in 17 seconds to get to the LAV maneuver. Went through that whole maneuver in 5 seconds. The jettisoned. The crew capsule was released where it was supposed to. The chutes came out, it floated down to ground, and it was beautiful.
The heavily instrumented capsule hit the ground 2 minutes and 14 seconds after launch, 6,919 feet from its takeoff point. Touchdown velocity was 16 miles per hour, about 6 miles per hour slower than predicted.
When we recovered the crew module from pad abort 1, it was in perfect shape. In fact, the project wants to reuse it again on another flight test, and it was never in the original plan to reuse the crew module. It was assumed that it would at least be charred up to some extent, and maybe even hit the desert at a velocity such that you'd damage the structures. But the parachutes performed so well and the thing touched down so gently. The avionics, all the electronics in there were still running. If you look at it externally, you'd say, wow, it looks like it was never even used.
It's probably one of the most thrilling times in my career to finally see something launch that you have worked on so hard with your team. The team that we have is excellent. And to finally see it go and go with such perfection was just almost indescribable, honestly.
I guess I was both very proud of the accomplishments of the team. Everybody had worked very hard, especially there towards the end, to get to the flight test, to a successful flight test, and see all that hard work pay off in what looked to be almost flawless flight test. But also there was some relief in that everything had gone well, because part of engineering is both trying to tackle the big issues that are concerns, but also trying to make sure that there's nothing that you've missed, that could be out there that could be a gotcha and that could really hurt you. So it was relieved that we'd been able to cover all the bases.
Well, in one of the subscale static tests, we had a failure of the panel, and so the panel was beefed up quite a bit. And we made that change and went into some full-scale static test of all 8 valves simultaneously, which is quite remarkable, going from just 2 valves at a time to 8. And then also trying to incorporate the controlling hardware into that and make them all perform a symphony of thrust that comes into what we call the duty cycle. So that was quite remarkable and quite a large feat to have all that come together at one time, and we did that successfully in 2 static tests.
Just seeing it do its job, shooting up into the, up into the sky, controlling the abort motor, and it looked like it was doing it, seamlessly. And it was great to see all those years of work and the hours that we spent go to such a monumental event like that.
Yes, it worked. Everybody has something in mind, and it was to make this thing work. And when I saw the LAS going over, I said, wow, we have a heck of a team. There's a lot of brain power behind this design and flight. So it was awesome.
To get to the next generation of space exploration, scientists, engineers and administrators agree that the recent tests of the LES was an astounding success, and a major reason for its success was the men and women behind the project.
Just the point of being part of a team that worked together, basically went through an entire project life cycle to achieve that goal, and it was a really neat feeling.
This is good evidence of how NASA cooperates between centers. We are driving ever more towards being one NASA. There are many NASA centers, but those centers have to function as one entity, and there has been a large learning curve in the last 3 years, but the last year I feel has been exceptional performance between Marshall, Houston, and Langley in terms of Langley leading, Marshall providing propulsion, and Houston providing program-level interface to the rest of the vehicle.
We have not done a controllable solid like this at NASA, and now that we've started and we've gone this far with the motor, I can see us using it in other applications. I could see us, maybe using it on commercial flights in the future. There's just a lot of new opportunities because this is a new concept that we haven't tried here at NASA. So I'm really excited to be a part of that.
It's quite an achievement, and the technology that we've developed in this program, most specifically the Abort motor and the attitude control motor, are very unique, and certainly could be used in any launch abort system that we'd come up with, a constellation program or whatever's in the future for NASA.
I've thought about the success of this team and how we've all labored together, the partnership, Marshall Space Flight Center with Langley Research Center, how we are working for Johnson Space Flight Center and the Flight Test Office, our prime contractor Lockheed Martin, their major sub-orbital sciences, ATK Utah, ATK Elkton, and Aerojet, everyone with one goal in mind. Let's make this crew escape system work in case it ever has to be used, which we hope it never has to be used, but if it does, it's not going to fail because of us, it's going to work.
As the United States and other countries continue our exploration beyond Earth's gravity, the safety of future space travelers was taken a step further in saving lives by NASA's state-of-the-art LAS, the highest thrust and fastest acceleration launch abort system of its kind in the world ever tested.
Just a great experience to see that go from, paper 4 years ago to that launch, which was just picture perfect, just an excellent launch. It was just a great experience to be out there for that and to witness that.